Mm-hmm.
If there's like, like in the bottom of the fraction, it's like negative x. Does that mean negative 1 and then the parentheses x minus 3? So you have to take the negative out.
Hold on, I don't think I have. Let me pull up. You would factor the bottom, so you'd say 1 over negative x minus 3. So 1 is normal. If you see a 1, that's standard, so there's no stretch, no compression. And then here you'd say reflect over y, right 3, and then up 5. And this one would have a vertical asymptote at positive 3, x equals positive 3, horizontal asymptote at y equals 5. Yeah. So if you look at your notes, it's a rational function. Rational functions have a 1 on top, or the a and the b, right? So 1 is normal, another number is not. This number is the vertical asymptote, x equals h, and it's the opposite sign, so our problem had a minus 3 in it, which means positive 3 is what it would be, so x equals positive 3. The number on the end is a horizontal asymptote, so y equals the number on the end, which was 5. Asymptotes for rational and asymptotes for exponential. So only 2 problems have asymptotes. Rational and exponential have horizontal asymptotes, and it's the number on the end. It's the k value, the number on the end.
What if it's a negative?
Then it would be a negative value.
Well, I mean, I don't understand the asymptote.
Asymptote is just a line that you get really close to and don't cross. And it's always the number on the end. So, and it's exactly what it looks like. So if it says plus 3, then it's a 3. If it says minus 2, then it's a negative 2. It's just exactly the number on the end. The vertical asymptote is only for the rational functions, and it's just the opposite sign of the number. So if this said x plus 5, it'd be negative 5. If it said x minus 3, it'd be positive 3. So when you work on this, definitely keep your notes out and then turn back to your notes often. Yeah, the notes are going to be helpful. Okay, any other questions? Anything else that showed up on the assignment that was weird or confusing? Okay, let's go ahead and turn to the domain and range. We're actually going to look at domain and range this time. So we knew this is an exponential function. That means it has a horizontal asymptote at negative 3, so we drew that in yesterday. So now we can go ahead and do the domain and range. And if you guys remember this from Unit 1, domain has to do with x values, range has to do with y values. I always like to write that big in my notes so that I don't have to read the small definition. I can just see it at a glance. So that means that domain, if it's x values, it's me looking at the picture from the left to the right. So if I look from the left to the right, I see that the left side is an arrow, the right side is an arrow, and there's no gaps in the graph. The graph is just nice and smooth, it's continuous. I can just follow it with my finger, there's no gaps. I know it's going to keep going forever this way. It's going to go to the right kind of slowly, but it is going to go forever. So what number do we use for a left arrow? What number represents left forever? Negative infinity. And what number represents right forever? Infinity. So the domain is negative infinity to positive infinity, or all real numbers. For the range, we're doing the y values. So we're going to go from down to up. So I can see that for down, it goes down forever. I have an arrow pointing down. For up, I can see that there's an arrow, but that arrow never gets past the dotted line. It never touches the dotted line because the dotted line is an asymptote. So it goes down forever, but it doesn't get past whatever number the dotted line is. So down forever up to the asymptote. So what do we write for down forever? Negative infinity. And then what number do we write for the asymptote? negative 3. So I'm going to put a parenthesis around the negative infinity because I'm never actually going to be able to put my finger on negative infinity and say there, that's where I hit negative infinity. Am I ever going to be able to put my finger on a point where the graph hit negative 3? Does it touch negative 3? No, so I put a parenthesis there. So domain and range mean that those are values that are actually touched in the function. The domain is x values that the function touches. The range is y values that the function touches. So I put a bracket if that value is included. If I can touch that value, I put a bracket. If I can't touch that value, I put a parenthesis. So I include values that make that definition true. I put parentheses if I don't include values that make that definition true. So that's why these are both parentheses, because I can't actually touch them. Okay, make sense so far? So whenever we want the domain and range, we're going to have to see a picture of the graph, or else know the equations well enough that we can picture it in our head or draw a little sketch of it or something. So we're always going to graph those. All right, increasing interval and decreasing interval. This is where I typically draw a stick figure to help me figure out if the graph is going like uphill, which would be increasing, or downhill, which is decreasing. Increasing and decreasing interval, again, you can read this in the definition, but it always has to do with x values because these are x values that describe y values. So it is where x values make the y values go up, where, which is x values that make the y values go down. So I'm going to put my stick figure right here, and he is at a left arrow. What number is a left arrow? Negative infinity. And is he walking uphill or downhill? He's walking uphill. He's downhill from this point, but if he starts walking, he's going to be walking uphill towards that point. So he's walking uphill, because we always think about going from left to right. So he's walking uphill. And he's walking uphill to the locator point. Can somebody tell me what the value is for the locator point? We're not going to use this version, because this version hasn't been factored. We're going to use this version over here. -3, +6. So we're going to make sure that whenever we find the locator point or find the vertex, that we're always using the version that we were able to find the transformations from. Does that make sense? We have to make sure that the inside of the function has been factored before we find the locator point, or our x-coordinate could be wrong. Okay, so our locator point is -3, 6. So what is the x value right here? -3. Okay, so for the increasing interval, the word increasing is written in between which numbers? -infinity and -3. Okay, now the definition of increasing is like it's where the stick figure is walking uphill. So if the stick figure is walking uphill at that number, and I can see that number, then I put a bracket. If the stick figure is not walking uphill at that exact number, then I put a parenthesis. Infinity is never a number I can see, so I always put a parenthesis at infinity no matter what. There is never a point where you will ever put a bracket on an infinity. Okay? Now, at -3 right here, is the stick figure walking uphill when he gets right there? Like walking uphill? Yeah, it's not an in-between. So if you think about last unit, we had, or the unit before last, we had this as a point in between. And here we would have put a parenthesis because when you get to the top, you're kind of in between uphill and downhill. So if you were standing right there at the top and someone said, "Are you walking uphill?" You'd be like, "Well, I just got uphill. I'm not actively walking uphill when I get there." But here, I would say I'm not in between uphill and downhill. I'm still on the uphill portion. Does that make sense? The only part when I get done is when I'm like past that and I like drop off the cliff, I guess, is how you could think of it. So we're going to put a bracket there because we're going to say this point is included. That's like the best description I can give you. Does that kind of make sense? So this one we would say we would not include. This would be a parenthesis because it's in between uphill and downhill. It's kind of like a neutral space. This one we're going to put a bracket because we're including it. It's part of walking uphill. Okay, for decreasing interval, do you guys see any part where it's decreasing? No? So we don't leave that blank, we say none. We don't leave it blank, we say none. So once you've done increasing and decreasing intervals for a while, you might get to the point where you can do them in your head, but typically it's good to draw a picture. And when students ask me for help, it's almost always because they have not drawn a picture and labeled it. So if you need help on this, the first thing I'm going to ask you to do is draw a picture and start putting the labels in. Like put the stick figure in, right where it's uphill, right where it's downhill, and usually students can figure it out for themselves. All right, maximum and minimum, we're going to write these as a point. So we're going to write this as an X and a Y coordinate. An X and a Y coordinate. So maximums look like mountaintops, minimums look like valleys. Which one does this graph have? It has a minimum. So for maximum, I'm going to put none. And for minimum, what am I going to put? Don't look here. We have to look where we looked after we found the transformations. -4, -1. So the minimum is also the vertex. And it would be -4, -1. All right, x-intercepts and y-intercepts, you guys know what those are. We just have to make sure we can find them in these graphing calculators. So where the graph crosses the x-axis, where the graph crosses the y-axis. So let's get our calculators out. And I'm just going to press the y equals button because I'm going to type this in. You can type 1 divided by 3 for the 1/3, or if you want to type it in as a fraction, you can type alpha y equals, that's how we get a fraction. So alpha y equals, and press enter, and that's how you can get the fraction 1/3. So x plus 2, and then remember to get another exponent other than a squared, we use this up arrow right here, which is the caret button. I'm pretty sure that's what they call it. And you can press graph. And it's very close. It looks like it might be exactly on -3. I'm not sure. Usually when my x-intercept is on the left side of the graph, I tell my calculator to look between -10 and 0. But you could be more specific. You could say, oh, if it's at -3, we should look between -4 and -2. You can be as specific as you want. So to find the x-intercept, we're going to do second trace number 2. And it's going to ask us to look between a number on the left side of the answer and a number on the right side of the answer. In fact, since there's only one answer, you could tell the graph to look between -10 and +10. Then the exponential graph, this graph is continuous, because I can trace it with my finger and get the whole thing. So I put that in the notes, that they're all continuous except for rational functions. And they are all always continuous except for rational functions, which are never continuous. Okay? Does it make sense for what continuous means as far as like being able to trace it with your finger? So just being able to trace the whole graph at one time without picking up your finger, that's all that it means. Okay, the next thing is end behavior. This is just describing what the arrows are doing. And it's not all the arrows, it's specifically the arrow on the left side and the arrow on the right side. And then on this one, this is a square root curve. And so the square root curve, like it doesn't have a left arrow. I'm gonna write no left arrow. There is no left arrow, but here's the right arrow. So that's what end behavior is doing, is it's describing what the left arrow is doing and what the right arrow is doing. So for the first example, we would say as x goes to negative infinity, this is us describing the left arrow. And for a lot of the graphs, you would say, oh, the arrow's going up or the arrow's going down. And then you could say if the arrow was going up, you would say that y was going to positive infinity. If the arrow was going down, you would say that y was going to negative infinity. But I wanted to use this rational graph as an example because these arrows are not going up or down. Where are these arrows going? Yeah, they're going to the horizontal asymptote. Do you guys see that? They're not going up or down, they're going to the horizontal asymptote. So we're going to write this over here because this is one that students tend to struggle with. The horizontal asymptote is the line y equals k. So for this one, on the left side, if the y value is not going up forever, it's not going down forever, it's actually going to that k value. So we would say as you look to the left, as we look at the left arrow, we're going to see that y is going towards that horizontal asymptote value of k. Not up, not down. It's going to level out at k. Same thing for the right arrow. So if we look at the right arrow, we're going to see as x goes to positive infinity, that means we're looking at the right arrow. The y value is doing the same thing. It's not going up, it's not going down. It is leveling out in the middle at the k value. All right, now for this one, if you tried to look at the left arrow, you would get confused because there isn't one. And so we're going to say, as we look for a left arrow, we're going to say y is undefined. As I look for a left arrow, I see nothing because y isn't defined there. I can do inputs for the graph. I can try to plug in x values to infinity, to negative infinity, but my outputs are not going to work. I'm going to get error messages for my outputs. That's what that means. I can look at the right arrow, though. What do you guys notice about the right arrow? Is it going up or down? Down. What kind of number is down? So I'm going to say, as I look at the right arrow, as x goes to positive infinity, y goes to negative infinity. My right arrow is also a down arrow. My right arrow is also a down arrow. So when you describe end behavior, you're just describing what the arrows are doing. If an English teacher was describing what the arrows were doing, they would use words. A math teacher, when they describe what the arrows are doing, they're going to use math symbols. So these are math symbols that just don't use words. Does that make sense? Okay. So now we're going to go ahead and go back to the assignment that we had. So if you get past that first page, now what I've got is there's instructions that ask you not to find everything, but just to find two things for two different functions. So for the first one, it says domain and range and the intercepts, x and y intercepts for those two functions, then increasing, decreasing, and intercepts for the next two functions, vertex and end behavior for the next two functions. So it's kind of a mixture. And for a lot of these, you're probably going to need to get the function that you're looking at into that transformation form first. So when I look at number 15, I probably wouldn't look at that as negative 2 to the 3x plus 12 plus 2. I would take that 3x plus 12 and I would factor it. Not because I'm going to need that for every single problem, but because it's a good habit to get into. so that if I did need the locator point, if I did use that to help me find something for the domain and range when I do that by hand, if it was important, then I do have it in that form and I'm not accidentally forgetting to do that. Does that make sense? So what I would do is when you first get started on these problems, look at the inside of the function. So the inside of this one is the exponent. The inside of this one is the inside of the absolute value part. The inside of this one is the inside of the parentheses, the inside of the square root. I would look specifically at the inside of each function and see if it could be factored, and start off just by doing that so that you can clearly see your transformations and clearly see your vertex or locator point before you do what the rest of the problem is asking for, just in case you need it. Because we saw when we were doing these notes that we didn't necessarily need it on every problem, but here the locator point helped us to find the increasing and decreasing intervals. Here the locator point helps us with the maximum or minimum. And so sometimes it can help you and you don't realize, but it would have been easy to get those answers wrong if we hadn't found it ahead of time, what those transformations, how they adjusted the equation. Does that make sense, what I'm saying? That it can impact your answers and you wouldn't necessarily think about it. Okay, so get to work on that, and then let me know when you guys are starting to finish up those assignments, and we'll start looking at the next thing. Okay?